The stars are moving, not drifting, not tumbling, but slipping away. Each galaxy, a lantern on a night sea, sailing outward into silence. Not falling, but accelerating. The farther they are, the faster they flee, as if space itself is stretching. As if the very void between all things is pulling apart. No hand pushes, no wind blows. And yet, the universe expands. Not just from a past explosion, but from a force no one can see. A whisper in the fabric of reality. A presence made only of absence. They call it dark energy. But no one knows what it is. Not matter, not light, not even shadow. Just a pressure, a breathless push, a gravity made of nothing. We thought the cosmos would slow, that gravity, patient and persistent, would pull it all back in. That the universe, born in fire, would one day fade in stillness. But the sky betrayed us. In 1998, we looked deeper, measuring the light of ancient stars, and found a surprise. The universe isn't slowing down. It's speeding up, as if some hidden force is working in reverse, as if the void itself wants distance, wants forgetting. What is this strange acceleration? What moves without moving? What expands without needing space? This is not just a question of science. It is a question of fate, because dark energy doesn't just shape what we see, it determines how it ends. Will the galaxies vanish into cold separation? Will the stars burn out into eternal darkness? Or will the very atoms that form us be torn apart by the gentle hand of a force we cannot name? In this final chapter of our cosmic journey, we follow the gravity of nothing, the force that built the silence between the stars and may one day silence them all. There was a time not so long ago when we thought we knew how the universe would end. Gravity, the silent sculptor of stars and structure, had always pulled. Invisible and patient, it shaped everything from the fall of apples to the swirl of galaxies. It wove the cosmos together like a thread through cloth. It was the force of return, the promise that what flies apart may someday fall inward. For nearly a century, astronomers believed that this gentle tug would gradually slow the universe's expansion. It made sense. The Big Bang had given the cosmos its outward momentum, but gravity, we thought, would be the brake. Sooner or later, the expansion would halt. Perhaps it would freeze in place. Perhaps it would collapse. But never was it expected to accelerate. That changed in the 1990s. Two teams of astronomers, working independently, set out to answer a simple question. How fast is the universe slowing down? To do this, they used the cosmos's most reliable lighthouses, type Ia supernova. These stellar explosions are not just bright, they are consistent. So consistent, in fact, that they can be used as standard candles. By comparing how bright they appear to how bright we know they are, we can estimate their distance. By measuring the redshift of their light, the way it stretches as the universe expands, we can tell how fast they're moving away. The logic was elegant. Measure many supernovae at different distances, and you can trace the expansion history of the cosmos itself. But what they found wasn't just unexpected, it was unsettling. The most distant supernovae were not where they should have been. They were too dim, not because they were obscured or fading, but because they were farther away than expected. Much farther. That meant they had traveled farther in less time, which meant the expansion had not been slowing it, had been speeding up. The universe wasn't coasting, it was accelerating. This result was so shocking that the scientists double and triple checked their data. Could there be interstellar dust interfering with the light? Were the supernova somehow evolving over time? But no matter how they looked at it, the conclusion remained. Something was driving galaxies apart faster and faster. This was not just an observational quirk. It was a transformation in our understanding of the universe itself. And so, with no better name for it, they called it dark energy. Not because it was dark, it's not because it was energy in the traditional sense, because it was unknown, invisible, mysterious. Dark energy didn't fit into any of our tidy models. It wasn't like dark matter, which at least had gravitational fingerprints. It wasn't like regular energy, which radiated or heated or pushed against things in familiar ways. Dark energy didn't clump, didn't glow. It didn't even seem to care about matter at all. Instead, it acted as a property of space itself. It's not something inside space, but something that is space. Every cubic centimeter of vacuum, no matter how empty, might carry with it a tiny amount of this strange energy. And as the universe expands, the amount of space increases, so the total dark energy increases too. In other words, the more the universe grows, the more dark energy it contains, and the stronger the push becomes. This is not like any other force we've ever known. It does not weaken with distance. It does not fade with time. It compounds. It's like a gentle hand on your back, barely noticeable at first. But with each step forward, it presses harder until you're no longer walking, but running, then sprinting, then soaring into a night that has no edge. By the early 2000s, dark energy had gone from shocking anomaly to centerpiece of cosmology. Observations from the cosmic microwave background, the relic light from the Big Bang, confirmed it. Measurements of large-scale structure, baryon acoustic oscillations, and galaxy cluster surveys all pointed in the same direction today. Dark energy is believed to make up about 70% of the total energy content of the universe. Let that sink in. Everything we've ever touched, seen, or measured, every atom in every star, every planet, every cell in your body makes up less than 5% of the cosmos. Dark matter accounts for about 25%, and the remaining majority. This silent, invisible pressure, we still don't understand. This wasn't just a revelation, it was a humbling. We thought the universe was made of things, matter, particles, forces we could test. Instead, the cosmos appears to be made, in large part, of something that does nothing we can measure except make space grow. Some try to explain dark energy as Einstein's cosmological constant, a term he introduced, then abandoned. Originally, he'd inserted it into his equations to keep the universe static. But once the expansion of the universe was discovered, he called it his greatest blunder. Now, it seems, it may have been his most profound insight. A cosmological constant is simple, at least in theory. It's a constant energy density built into the very structure of space. As space expands, this constant doesn't dilute. It stays the same per unit volume, so the total energy increases as space increases. It's the ultimate feedback loop. More space means more dark energy. More dark energy means more expansion. More expansion creates more space, and the cycle continues. There's no switch, no origin, no off button. It just is. This runaway effect is what now defines our future. The destiny of the cosmos is not decided by stars or black holes, but by the quiet, invisible pressure of the vacuum. But this idea of the vacuum being not empty, but active, was not entirely new. Quantum field theory, the framework of modern particle physics, has long held that even the emptiest space is a sea of activity. Virtual particles blink in and out of existence. Fields oscillate at their lowest energy levels. What we think of as nothing is actually a roiling sea of fluctuation. And yet, when physicists calculated the expected vacuum energy from quantum theory, the number they got was too large, not slightly off, more than 10 times larger than what we observe. This is often called the worst theoretical prediction in physics. It's not just wrong, it's mind-bendingly wrong. If vacuum energy were truly that large, the universe would have torn itself apart in an instant after the Big Bang. Nothing could have formed. Not stars, not atoms, not time. So something is off. Either our theory of quantum fields is incomplete, or something else is suppressing the vacuum energy we expect. And until we understand that, dark energy remains not only unexplained, but possibly the key to a new physics we haven't yet imagined. It's rare in science to discover something this fundamental by accident. But dark energy was just that. It wasn't predicted. It wasn't hunted. It was found in the leftover light of dying stars, quietly revealing a universe with different rules than we thought. And perhaps that's the lesson. The universe does not owe us simplicity. It does not bend to expectation. It expands, because that is what it does. And in its expansion, it writes a new chapter not in fire or fury, but in a whisper. A whisper we're only just beginning to hear. We tend to think of space as a backdrop, a vast nothingness between stars, a cosmic stage on which the galaxies perform. Empty, quiet, inert. But what if that emptiness wasn't empty at all? What if the vacuum of space wasn't the absence of everything, but the presence of something hidden, patient, and immeasurably powerful? This is where the mystery of dark energy grows deeper. Because one idea, perhaps the simplest of them all, is that dark energy isn't something exotic or new. It's just the energy of empty space itself, a vacuum. With teeth, Albert Einstein modified his equations of general relativity. At the time, it was thought the universe was static, neither expanding nor contracting. But his equations, in their raw form, predicted collapse. Space wanted to move, so Einstein introduced a new term, the cosmological constant, a mathematical adjustment that would perfectly balance gravity, keeping the universe frozen in stillness. It was elegant, it was precise, and it turned out to be wrong. In the 1920s, Edwin Hubble observed that galaxies were moving away from us, proving the universe was expanding. Einstein retracted the constant, calling it his greatest blunder. But decades later, after the discovery of cosmic acceleration, scientists brought the cosmological constant back, this time as a way to explain the gentle, persistent push of dark energy. Not a mistake, but a hint. Perhaps space itself had a built-in pressure, a kind of cosmic elasticity. To understand this, we must go deeper into the strange world of quantum fields. Modern physics tells us that every particle is a ripple in a field that fills all of space. There is a photon field for light, an electron field for matter, a Higgs field that gives mass. These fields are not confined to atoms or stars. They extend everywhere, even into the vacuum. And in the quantum world, even the vacuum is never truly still. Particles flicker into existence and vanish again, too fast to be directly seen. These are virtual particles, ghostly blips that exist in the equations, if not in the detectors. Fields vibrate constantly, even at their lowest energy state. What we call empty space is a seething foam of activity full of fluctuations, possibilities, and fleeting events. This gives rise to a strange idea. Even nothing has energy. The energy of the vacuum isn't zero. It's the sum of all those jittery little fluctuations. And if that's true, then empty space has weight, pressure, consequence. In other words, vacuum energy. This idea makes intuitive sense. If space is never truly empty, if it's always alive with fields and flickers, then it's not a passive stage. It's an active player in the universe. Vacuum energy would behave in exactly the way dark energy does. It would be spread evenly through space. It wouldn't clump. It wouldn't fade. It would grow in total strength as the universe expanded. And it would exert negative pressure, a repulsive force that drives expansion. That's not speculation. That's exactly how the math works. The more vacuum you have, the more push you get. So if vacuum energy explains dark energy so perfectly, what's the problem? The problem is scale. When physicists calculate how much energy the vacuum should have based on quantum field theory, they get a number that's catastrophically wrong. Not a little off, not even by a factor of 10. They get a result that is 10 to the power 120 times too large. That's a 1 followed by 120 zeros, a number so enormous, it's almost beyond comprehension. It would imply that the universe should have blown itself apart in the first instant after the Big Bang. Galaxies couldn't form. Matter couldn't stabilize. Even time itself wouldn't stretch far enough to hold meaning. Clearly, that didn't happen. But we don't know why. This discrepancy between the vacuum energy we expect and the dark energy we observe is often called the worst theoretical prediction in the history of physics. And it's not just a fluke. It's a sign that something deep in our equations doesn't fit. Some believe there must be a mechanism that cancels out the vacuum energy, some hidden symmetry that subtracts away most of it, leaving just a tiny residual amount, the sliver we observe as dark energy. Others propose that we're thinking about space all wrong, that maybe, just maybe, gravity itself is incomplete. After all, general relativity and quantum field theory are titans that have never fully reconciled. They are two different languages describing the same cosmos, one with smooth curves and warps, the other with jittery probabilities and discrete units. Perhaps the conflict between dark energy and vacuum energy is the universe's way of telling us, you need a new grammar. And still others turn to the multiverse. In a universe where countless other universes may exist with different physical laws, constants, and vacuum energies, it may be that we live in the rare pocket where vacuum energy is just small enough to allow stars and galaxies to form. Too large, and everything flies apart too fast. It's too small, and the universe collapses before life can begin. Somewhere in the middle, we emerge. This is the anthropic argument, controversial, often resisted, but not easily dismissed. We may not live in the best universe, we'll live in the one that permits us to ask why. To understand why the vacuum drives expansion, we must confront a strange truth. In Einstein's universe, pressure matters as much as mass. In our everyday world, we associate gravity with weight. The Earth pulls you down because of its mass. The more mass, the stronger the pull. But in Einstein's equations of general relativity, gravity isn't caused by mass alone, it's caused by energy and pressure combined. That's because gravity is not a force in the traditional sense, it's a warping of space-time itself. Imagine the universe as a fabric. Mass creates indentations, curves. But pressure, especially pressure that's uniform, and negative can stretch the fabric like a balloon inflating from the inside out. This is what dark energy does. It behaves like a fluid with negative pressure. And unlike normal pressure, which resists compression, negative pressure pulls outward, not on objects, but on space itself. It's counterintuitive. We're used to gravity pulling things together. But dark energy doesn't act like gravity. It is gravity just in reverse. It's what happens when the vacuum isn't passive, but dynamic. Not content to remain still, but compelled to grow. And that growth, quiet, constant, cosmic, is why the expansion of the universe is not slowing, but speeding up. But what is this pressure really? In physics, pressure is energy density per unit volume. For ordinary matter, as space expands, energy gets diluted. As photons stretch and lose energy, gases thin out. But vacuum energy doesn't behave that way. It stays constant per unit volume. As the universe grows, more vacuum appears, and with it, more energy. The total amount of dark energy increases. That's like building a staircase where every new step is taller than the last. Each moment of expansion doesn't just continue the trend, it amplifies it. And so, the more space there is, the faster the universe expands. The faster it expands, the more space is created. The more space, the more dark energy, and on and on. This is what cosmologists call exponential expansion. Not a gentle drift, a runaway process. An accelerating separation that pushes galaxies apart until even light can't bridge the distance. It's not a loud process. There are no explosions, no cataclysms, just silence, just cold, just the slow erasure of connection. And yet, this still might not be the strangest part, because some physicists believe that even this vacuum, our current, stable-seeming vacuum, might not be permanent. It may be metastable, a temporary state, one that appears stable over billions of years, but could eventually decay into something else. This idea comes from the standard model of particle physics. When you plug in the numbers, especially the mass of the Higgs bosonet, suggests that our vacuum might not be the lowest possible energy state. There may be a deeper, more stable vacuum out there, a true vacuum. And if that's the case, our universe is living on borrowed time. Because in a metastable vacuum, there's always a non-zero probability that somewhere, a quantum fluctuation could trigger a transition. A bubble of true vacuum could form. Small at first, but expanding at the speed of light, is consuming everything in its path. In that bubble, the laws of physics would be different. The constants we rely on would change. Particles could gain or lose mass. Forces could behave differently. Chemistry, biology, structure, everything would be erased. Not with violence, but with indifference. A vacuum decay would be the ultimate reset. No warning, no resistance, just transition. Now, it's worth noting, this is only a theoretical possibility. There is no evidence that such a vacuum decay is imminent. The universe has survived for billions of years. And if we're truly in a metastable state, it might endure for trillions more. But the idea is haunting, not because it's likely, but because it's allowed. It reminds us that even the firmest foundations of reality may not be absolute. That even nothing is not neutral. It can shift. It can surprise. It can end. And it shows us something deeper. That in the cosmic hierarchy of things, emptiness is not absence, it is agency. This turns our assumptions inside out. We once thought the vacuum was the lowest form of being, a baseline, a zero. But what if the vacuum is not the end of energy, but its origin? What if the void is not the silence after the music, but the breath before the note? The more we study the vacuum, the more it resembles a stage with tension, a fabric pulled taut, still, until it's not. And dark energy may be the visible edge of that tension and outward pressure that signals something hidden beneath. Waiting, humming, expanding. This changes how we think about reality, about stability, about permanence. Because if even nothing can change, then everything can. And in that possibility, terrifying as it is, there is also wonder, because the story of the universe is not just one of stars and galaxies. It is also the story of space itself, of a vacuum that breathes, that pushes, that grows, and perhaps one day, that resets. In this part, we explored how pressure shapes gravity and general relativity, why vacuum energy leads to accelerated expansion, the discrepancy between predicted and observed vacuum energy, the possibility that the vacuum itself may not be stable, and the philosophical implications of a universe where nothing is dynamic. We are not watching the universe expand from the outside, or inside the expansion, carried by a force not of matter, but of meaning, a pressure from the void, a whisper from the vacuum, a gravity made of nothing. What if dark energy is not a constant? What if it's not even energy? What if the accelerating universe is not being pushed by something new, but pulled by something we've misunderstood all along? For all its elegance, the cosmological constant is a blunt instrument. It fits the data, but it explains little. It's a single number that fills space with pressure. But nature rarely paints in simple strokes. The closer we look, the more subtlety we find. And for some physicists, the idea that dark energy is static, unchanging across time and space, feels incomplete. Instead, they ask, what if dark energy evolves? What if it flows like a river, changes like a season, pulses like a heartbeat? Enter quintessence, a name borrowed from the ancients, who once believed a fifth element pervaded the heavens. Today it refers to a different kind of force, a scalar field that changes over time. Like the inflatoned field believed to have driven the early universe's rapid inflation. Unlike the cosmological constant, which remains fixed, quintessence can vary, its energy density rising or falling as the field rolls through space. This makes it dynamic, potentially detectable, and deeply compelling. It's also entirely hypothetical, but its appeal lies in its flexibility. A field that evolves could explain why dark energy is small today. Perhaps it was stronger in the past or may vanish in the future. Perhaps it will reverse, slow the expansion, or end it. In this view, dark energy isn't an intrinsic property of space. It's something more like weather, localized to the cosmos, driven by hidden forces we can't yet detect. But what if the problem isn't energy at all? What if it's our understanding of gravity that's flawed? General relativity has passed every test within the solar system, from the precession of Mercury to the bending of starlight. But those are tests of strong gravity over short distances. What if the laws that govern galaxies and planets don't quite apply to the vast intergalactic void? This is the idea behind modified gravity. Some theories suggest that gravity becomes weaker or stronger over large scales, that it leaks into extra dimensions. That space curves not just in response to matter, but to more subtle geometrical effects. In these models, there may be no need for a separate force or field. The apparent acceleration we see could simply be the natural behavior of gravity at cosmic distances. It's a tempting idea. If true, it would eliminate the need for dark energy altogether. But it's also extraordinarily difficult to prove. The universe is not a lab. We cannot isolate variables. We cannot run controls. Still, experiments continue, using gravitational lensing, galaxy clustering, and cosmic background radiation to test whether gravity's reach is truly universal. If dark energy evolves, if it changes with time or varies with location, then the key to understanding it may lie not in the equations, but in the sky. Cosmologists have spent the last 2 decades mapping the universe in exquisite detail, measuring how galaxies cluster, how the cosmic web stretches, how the light from the early universe fluctuates. These observations form a kind of cosmic seismograph, sensitive to the tiniest shifts in the expansion rate of space. One method is to look at baryon acoustic oscillations, ripples in the distribution of galaxies left over from sound waves in the early universe. Another is to measure the cosmic microwave background, which acts like a fossil snapshot of the universe just 380,000 years after the Big Bang. These tools let scientists compare the rate of expansion at different epochs, creating a kind of timeline of acceleration. If dark energy is truly constant, the timeline should follow a smooth, predictable curve. But if it evolves, if it waxes or wanes over time, those subtle differences would appear in the data. So far, no clear deviation has emerged, but the margins of error are shrinking. And even now, there are hints, barely significant, but suggestive, that dark energy might be getting stronger. That would be no small thing. A universe with an increasing dark energy component could accelerate faster and faster until every galaxy, every star, every molecule, even the atoms themselves, are torn apart in what's known as the Big Rip. Not a slow fading, but a runaway unraveling. We're not there yet, but the data is still coming in. The mystery remains unresolved. Meanwhile, some scientists are asking an even deeper question. What if the universe isn't three-dimensional space evolving in one-dimensional time? What if there are more dimensions, hidden ones curled up beyond our perception? In string theory, the fundamental building blocks of reality are not particles, but vibrating strings, tiny loops of energy that require extra spatial dimensions to function. These dimensions are thought to be compactified, curled up at scales far smaller than atoms. But in some variants of the theory, gravity is the only force that can access these extra dimensions. That means gravity might appear weak in our universe because it's leaking into others. If that's true, then what we call dark energy could be the result of gravitational effects spilling in from higher dimensional space. It's not a new force, it's just an unseen geometry. In this view, the expansion of our universe might be an illusion, caused not by a pushing pressure, but by a bending of dimensions we cannot directly observe. It's an idea both beautiful and haunting, that we are afloat in a deeper, multidimensional sea, drifting not by force, but by curvature. Still, there is another possibility. Perhaps dark energy is not a substance, not a field, not even a tweak to gravity. Perhaps it is an artifact, a consequence of how we're measuring the cosmos. Our models assume the universe is smooth and homogeneous on large scales, but the real universe is lumpy, clumpy, filled with voids and filaments and clusters. Some physicists suggest that averaging over these inhomogeneities might distort our view of cosmic expansion. What appears to be acceleration might be the result of observing a lumpy universe through a smooth lens. It's not a mainstream view, but it reminds us of a humbling truth. The map is not the territory. Our models, no matter how elegant, are still approximations. They are shadows of something larger. Hints of a deeper geometry we are only beginning to glimpse. At the heart of all these theories, quintessence, modified gravity, extra dimensions, observational artifacts, is a single question. Why does the universe expand the way it does? It is a question that strikes at the foundation of physics. Because if dark energy is real, then it is the dominant force shaping the cosmos. And yet it is invisible, undetected, and unexplained. It is the sound we cannot hear, but which moves the stars apart. And whether it is a substance, a field, a property, or a symptom, its existence challenges us to confront a possibility that is becoming harder to avoid, that our current picture of reality, our gravity, our matter, our space and time, is incomplete. In this part, we explored alternate possibilities beyond the cosmological constant. Quintessence with dynamic fields driving expansion. Modified gravity with possible breakdowns of Einstein's equations on large scales. Extra dimensions and gravitational leakage. And finally, the possibility that our methods or models themselves shape our conclusions. Dark energy may not be energy. It may be a signal, a boundary marker, a hint that the fabric of reality is not flat, but folded. And that what we call expansion is just the echo of a deeper truth, rippling through space and time. Let's continue with part 4, Clues in the Void of the Gravity of Nothing, Unveiling Dark Energy. In this part, we shift from theory to observation, unpacking the tools, maps, and signals scientists use to detect something they cannot see. We explore how the void, far from being empty, is laced with the evidence of expansion, and how reading that evidence brings us closer to understanding what dark energy truly is. Dark energy leaves no trace, no particle trail, no glow, no footprint, and yet its fingerprints are everywhere. In the curvature of ancient light, in the distances between galaxies, in the quiet swell of the cosmic void. To detect the undetectable, cosmologists have become cartographers of emptiness, charting the void not with compasses, but with light, with echoes, with the faint patterns left behind by energy that never wanted to be seen. This is not guesswork. This is cosmic archaeology. And the tools of this new science, though abstract, are exquisite in their precision. One of the clearest clues lies in the cosmic microwave background, or CMB. This is the oldest light we can see, a soft, uniform glow from when the universe was just 380,000 years old. Before that time, the cosmos was opaque, a soup of hot plasma. But as it cooled, it became transparent, and photons from that moment have been traveling ever since. Captured by missions like COBE, WMAP, and Planck, the CMB reveals subtle temperature variations, ripples that form the seeds of galaxies. But it also tells us about expansion, the angular scale of those ripples, how large they appear on the sky, depends on the shape and rate of the universe's growth. A faster expansion shifts the patterns, a slower one compresses them. The CMB is not just a snapshot, it's a ruler. And that ruler tells us something extraordinary. Around 5 billion years ago, the universe changed gears. The expansion, which had been slowing since the Big Bang, began to speed up. That shift, that cosmic inflection point, is the signature of dark energy. But we don't just measure the past, we also map the structure of the present. Galaxies are not scattered randomly. They form a web, a vast, sponge-like scaffold shaped by gravity and time. The distances between clusters, the density of voids, the length of filaments, these features encode the history of cosmic expansion. One of the key tools here is baryon acoustic oscillations, or BOEs. These are ripples in the distribution of galaxies' leftovers from sound waves in the early universe. Like circles spreading on the surface of a pond, these waves pushed matter outward in regular patterns. Today, that pattern survives as a preferred spacing between galaxies, about 500 million light-years. By measuring how that scale appears at different distances, scientists can trace how fast the universe has been stretching. It's like tracking a known yardstick across different parts of the sky. And the result? Yardstick grows longer over time not because it changes, but because space expands around it. Once again, the invisible hand of dark energy reveals itself not by showing up, but by changing the space between everything else. In a universe ruled by the unseen, light becomes our most honest witness. It travels in straight lines until space itself curves. It carries memories, until expansion stretches them into whispers. It marks distances not in miles, but in time. And so, astronomers use light not just to see the cosmos, but to measure the invisible forces shaping it. One of the most powerful techniques is gravitational lensing. First predicted by Einstein, lensing occurs when massive objects, clusters, even dark matter bend the space around them. Light passing through that warped space appears distorted, magnified, or duplicated. A single galaxy may appear as a ring. A distant quasar may show up in 4 places at once. To the untrained eye, it looks like cosmic coincidence. To the cosmologist, it's a window into the architecture of space. By analyzing how much lensing occurs at different scales, scientists can infer not only where mass lies but how the geometry of space is changing over time. And it's here in the gentle bend of starlight that dark energy again reveals itself. A universe expanding under the influence of dark energy bends light differently than one without. The more space grows, the more distance photons must travel, and the more the geometry distorts. Gravitational lensing turns the cosmos into a mirror curved not by glass, but by acceleration. Another beacon is the type Ia supernovae, the very tool that led us to discover dark energy in the first place. These are not ordinary explosions. They're thermonuclear outbursts triggered when a white dwarf accumulates too much mass from a companion star. When it hits a critical limit, it erupts with astonishing brightness. And here's the key. That brightness is predictable. So predictable, in fact, that type Ia supernova are known as standard candles. By comparing how bright they appear to how bright they truly are, we can measure their distance. Combine that with their redshift, the stretching of light due to cosmic expansion, and you have a two-part key: how far away it is and how fast it's moving away. In the 1990s, these exploding stars told us the universe was speeding up. Today, they continue to refine our understanding, measuring the expansion rate at different times in the universe's life. Each one is a time capsule, a light echo from a different chapter in the story of space. By observing hundreds, even thousands of these supernovae across billions of light years, astronomers build a timeline of acceleration, not guessed, but observed. And there's more. Some researchers now use cosmic time delays to measure expansion. When a quasar's light is lensed into multiple images by a foreground galaxy, those light paths take slightly different routes. They arrive at different times. By measuring the delay between flashes of light in those multiple images, scientists can calculate the geometry and expansion of space. It's a cosmic clock, built not with gears, but with light and gravity. And every tick, every lag between photons tells us about how fast the universe is growing. This method, known as strong lensing time delay cosmography, is one of the most precise and promising ways to constrain dark energy's behavior in the near future. In all these methods, lensing, supernova, time delays, the same truth emerges. Dark energy leaves no mark, but it shapes the path of everything else, like wind shaping dunes, like silence shaping music, like absence shaping meaning. It doesn't announce itself, it reframes the frame. In this part, we explored how cosmologists detect dark energy without seeing it. The CMB gives us a fossil map of the early universe. Baryon acoustic oscillations act as a cosmic yardstick. Gravitational lensing warps light and reveals geometry. Type Ia supernova measure expansion across time. Quasar time delays let us track acceleration with exquisite precision. The void is not empty, it is written with light, bent, stretched, and delayed. And in those distortions, the universe speaks the name of something it still refuses to show. The universe is not a static painting. It is a battlefield in slow motion. A vast tension hums beneath the quiet of space, visible, ongoing, relentless. Not a clash of armies, but of principles, of forces that do not see each other yet shape everything. On one side stands dark matter, the gatherer, the builder, the unseen sculptor of structure. It has no color, emits no light, interacts with no known particle in familiar ways. And yet it pulls. Its gravity binds galaxies together, forms clusters, strings, vast filaments of matter across the cosmos, like cosmic tendons. On the other side rises dark energy, silent, expansive, implacable. It is not a substance, but a pressure. Not a builder, but a separator. It does not clump. It does not cohere. It stretches the void between all things, slowly at first, then faster still. These forces are not antagonists in a duel. They are laws in opposition, one gathering, the other scattering. And for most of the universe's history, it was dark matter that led. In the aftermath of the Big Bang, everything was closer, denser. Gravity had the upper hand. Hydrogen condensed into stars. Stars gathered into galaxies. Galaxies formed clusters. And behind all this, quiet but vital, was dark matter. It was dark matter that created the invisible scaffolding, the framework on which baryonic, ordinary matter could cool and collect. Without it, the early universe would have remained a featureless fog, expanding, yes, but never coalescing into anything that could shine, rotate, or dream. Simulations show this clearly. Remove dark matter from the equations, and the cosmos fails to form recognizable structure. Galaxies unravel, filaments vanish. The beauty of the visible universe collapses into statistical dust. But structure is fragile. Gravity, while patient, is not alone. As the universe grew, it thinned. The web stretched. Gravity continued to pull, but with less urgency, less density to work with, less mass to anchor. Over billions of years, the scales began to shift, not because dark matter weakened, but because something else grew. Dark energy. It did not grow in strength. Space did. And dark energy is a property not of mass, but of space itself. Every cubic centimeter of vacuum carries with it this subtle pressure, and as space expands, there is more vacuum. More pressure, more push. Dark energy is not fast, it is not loud, but it is relentless. By around 5 billion years ago, it had taken over. The universe's expansion began to accelerate. The age of structure had ended, the age of separation had begun. To grasp what this means, imagine the universe as a grand architectural project. Begun with chaos, sculpted by gravity, built on scaffolding spun from dark matter. But just as the towers began to rise, a wind, unfelt at first, began to stretch the sky. This wind is dark energy. It does not destroy the buildings, pulls the ground out from under them, slowly, invisibly, but with results that, given time, become absolute. Galaxies that might have merged, as filaments that once tightened, begin to loosen. Structures that once coalesced never will. And it's not just a story of what might have been, it is a forecast. In the far future, the night sky will empty. It's not because stars die, but because they will live, receding beyond the horizon of what light can reach. This horizon is not a wall, but a boundary of causality, cosmic event horizon. Unlike the one surrounding a black hole, but this one encloses not a single star, but everything. As the expansion accelerates, galaxies beyond a certain distance become unreachable. Their light, no matter how fast, will never catch up. They drift not just away in space, but out of time as we can experience it. Eventually, the only galaxies visible will be those gravitationally bound to our own. Everything else will fade into undetectable isolation. To future observers, the universe will appear static, against cold, sparse, and inexplicably small. The history of expansion will be lost to visibility, only inferred, only imagined. We today stand at a privileged moment in cosmic history when the sky still holds its structure, when the evidence of what came before and what is yet to come is still written across the void. And that evidence is tension. The universe, in its vastness, is governed not by a single law, but by context. Scale changes everything. Zoom into a galaxy, and gravity reigns. Stars orbit their galactic center. Gas clouds collapse into suns. Even now, billions of years into the age of acceleration, the pull of dark matter holds galaxies together like stones sunk deep in space-time. Here, dark energy is too diffuse. Its hand, though everywhere, is too light to overcome the gravity stitched into the structure. Inside these halos, attraction still wins, but zoom out and the balance shifts. Between galaxies, dark energy becomes dominant. In the deep voids where matter is scarce and distances are vast, the expansion accelerates. Dark matter cannot reach across such emptiness, cannot build where there is nothing to bind. And so, structure fractures. The cosmic web stretches. The threads thin. The great clusters, once tightly woven, begin to drift. This is a universe in tension. Not one collapsing, but unraveling. Imagine two dancers connected by a ribbon. Dark matter pulls the dancers inward. Dark energy pulls the ribbon apart. At first, the tension holds. But as the ribbon stretches and the dancers drift, gravity's influence weakens. The connection thins. The steps slow, and finally, distance wins. What we're witnessing is not the destruction of matter. It is the loss of connection. It is not a war of force against force, but of proximity against scale. Dark matter can only pull what is close. Dark energy pushes across everything, and so the future becomes clear. Local islands of gravity floating in a sea of expanding space. Galaxies remain intact. Stars continue to burn. But everything beyond the reach of gravitational bonds, everything not anchored, drifts beyond reach. One day, long after the Earth is gone, long after the last star is born, the sky itself will change. Galaxies that we see today will vanish, not because they have ceased to exist, but because their light will no longer reach us. Their recession speed, driven by dark energy, will exceed the speed of light. They will cross the cosmic event horizon, leaving us in a bubble of ever-shrinking visibility. Eventually, only our local group, the Milky Way, Andromeda, and a handful of satellite galaxies will remain observable. This is not poetic metaphor. It is the consensus forecast of modern cosmology. The visible universe will contract, not because it is shrinking, but because everything else is accelerating away. And so, the great irony, the more the universe expands, the less of it we will see. What remains will be gravitational sanctuaries held together by dark matter, protected from the outward swell. These structures will persist for trillions of years, but they are islands in a growing ocean of void. Galactic collisions like the impending merger of the Milky Way and Andromeda will still occur. Stars will still be born. Black holes will still feed. But all of it will happen in isolation. Cosmic loneliness is not a philosophical fear. It is a physical inevitability. We are living in the twilight of the cosmic commons, a brief window, when the universe is still visible in its richness, and the cosmic web still connects. When the battle of forces is still unfolding in slow, majestic conflict, soon enough, one side will win, and the sky will grow quiet. This realization brings with it a strange emotion, not dread, not urgency, but reverence. To exist now when galaxies still thread the sky like jewels on velvet. To look up and see the reach of matter and the fingerprint of time is to stand in a privileged moment. We are witnesses to a chapter that will never repeat. The forces that shape this universe will continue their silent tug-of-war for eons to come. But we, as conscious beings, exist precisely when that battle is most visible. To see it is a kind of miracle. In this section, we explored how dark matter dominates locally, holding galaxies and clusters together. Dark energy dominates at large scales, driving the expansion of space itself. The universe is becoming increasingly disconnected, not destroyed. And our moment in cosmic history is one of rare visibility and wonder. We are not simply expanding, we are separating, held in place only by the gravity that built us, and surrounded by the vacuum that will eventually erase the view. Everything that begins, ends, or so we believe. We see it in the flicker of stars, the collapse of empires, the last breath of loved ones. And so we ask, what of this universe? This vast, expanding canvas of space, time, and memory? Will it stop? Will it shatter? Will it fade? The answer depends on one thing: dark energy. That quiet force pushing space to grow, faster, farther, colder. Because dark energy does not simply define what is. It defines what will be. It is not a footnote in the story. It is the final chapter. In the early days of cosmology, scientists believed the universe had two main options: expansion that slowed forever, or expansion that reversed into collapse. Gravity was assumed to be the deciding force. For a long time, the question was simple: will the cosmos freeze or fall? But that was before 1998. Before we discovered that the expansion is accelerating. Now the picture is different. Stranger, colder. Because an accelerating universe does not collapse. It does not slow, doesn't even coast. It drifts into emptiness. And so the most widely accepted fate today is something called the heat death. The name is deceptive. Heat death is not fire. It is cold. It is what happens when the universe expands so much that energy is diluted beyond usefulness. Stars burn out. Black holes evaporate. Gas clouds spread too thin to collapse. Matter decays. Even motion ceases. Entropy reaches its maximum. Structure becomes impossible. Time loses direction. There is no heat, no cold, just a flat, dark stillness. The universe becomes a featureless void. No stars, no observers. Only particles, scattered too far apart to interact. It is a fate not of violence, but of forgetting. A long, slow drift into silence, not with a bang, but with a fading. And yet, that may not be the only ending. If dark energy is not constant, if it grows stronger with time, the universe could meet a more dramatic fate: the Big Rip. In this scenario, the strength of dark energy increases exponentially. Not only does space expand, it expands so rapidly that it tears structure apart. First, galaxies are pulled from one another. Then stars from galaxies, then planets from stars, then atoms from molecules. And finally, space itself tears. It is the ultimate end of proximity. It's not just of matter, but of the laws that bind matter. The final moment is not cold. It is fragmentation. It is everything, everywhere, becoming alone. This could happen far in the future. Or, depending on how fast dark energy strengthens, much sooner. We don't know. Not all endings take their time. Some come not with a slow drift into silence, but with a rupture. Sudden, invisible, absolute. One such possibility lies buried in the heart of modern physics. A fate that does not wait for galaxies to fade or stars to burn out, but one that could arrive, now or never. It is called vacuum decay. And if it's real, it will be the last thing the universe ever experiences. To understand this, we must look not to stars or galaxies, but to the very foundation of physics. Quantum fields. Every particle in nature is a ripple in a field, an invisible sea that fills all of space. There's a field for electrons, a field for quarks, a field for light. At the center of this architecture lies the Higgs field, responsible for giving mass to particles. When physicists discovered the Higgs boson in 2012, they measured its mass with remarkable precision. And when they plugged that number into the standard model, something strange emerged. It suggested that our universe might not be in a true vacuum, the lowest possible energy state, but in a false vacuum, a local minimum, precarious valley that only seems stable till something triggers a fall. Imagine a marble resting in a small dimple on a mountainside. From where it sits, it appears stable, but just beyond the edge is a deeper valley. And if the marble ever gets nudged, it will roll irreversibly into a new reality. That is our universe. A marble in a false vacuum. And if it ever falls, if a quantum fluctuation, however rare, tips it over, then a bubble of true vacuum will form. At first, microscopic, but expanding at the speed of light. Inside the bubble, a new set of physical laws, a new value for the Higgs field, new masses for particles, new interactions, possibly even no structure at all. Atoms may not form. Chemistry may not exist. Time as we know it may unravel. And because the bubble expands at light speed, there will be no warning, no defense, no escape. The vacuum will decay, and the universe will be overwritten. This is not science fiction. It is a valid consequence of known physics, an implication of our best theories when taken to their logical end. And while some physicists argue that new physics might stabilize the vacuum at higher energies, others accept that metastability is real, that our reality is temporary. It's a strange, humbling thought. We often imagine the universe ending from without, by expansion, entropy, or cold distance. But vacuum decay suggests a different kind of ending, one that comes from within. From the very fabric we trust to hold everything together, there is no reason to believe it will happen soon. The probabilities are infinitesimally small on cosmic timescales. The vacuum may persist for trillions of years or longer, but probability is not certainty. And the mere fact that such a fate is possible alters the way we think. Because it means the universe doesn't just die of age, it can die of instability. A quantum sneeze, flicker, a reset. It challenges our idea of permanence. Now reminds us that even the most silent spaces are alive with risk, and that the laws of physics so stable today may only be temporary agreements. So now we've seen the futures, not one, but many, slow fading into stillness, a violent unraveling, quantum reset that arrives without warning. Each fate is different, each driven by the same quiet force, the gravity of nothing. And each demands we ask a question that no equation can answer. What does it mean that everything ends? For most of human history, the night sky was a symbol of permanence. The stars were fixed, eternal, beyond the reach of time. But we now know that the stars themselves are transient. Galaxies will fade, the sky will empty, and the laws we rely on, the ones that govern mass, motion, and light, may be fleeting patterns in a deeper sea we cannot see. It is easy to feel small in the face of this, to feel that impermanence is a kind of defeat, that our lives, our stories, our memories vanish like sparks in the wind. But perhaps impermanence is not a flaw. Perhaps it is the engine of meaning, because what matters is not that the universe ends, but that we are here before it does. To love in a universe that will forget us, to create, to wonder, to reach for understanding in a cosmos that offers no guarantees, is not meaningless. It is heroic. It is art. Every conscious moment, every act of empathy, every glimpse of awe becomes more precious, not less, when it is set against the backdrop of an ending sky. We are not here forever, but we are here now. And the now is luminous. In the end, the universe may go cold or tear itself apart, or be rewritten by a bubble of true vacuum. But the end, when it comes, will be quiet. There will be no one left to see it. No one to mourn what was lost. Only the echo of what once was, baked into the curvature of forgotten space. And yet from within this fading structure, a question rises. If nothing lasts, why does beauty still feel real? Why does love still matter? Why do we care so deeply for a world that is vanishing? The answer, perhaps, is this. Because even in a universe that ends, you're the part that knew it could. In this part, we explored the heat death, a future of stillness and entropy. The Big Rip, a future torn apart by runaway expansion, vacuum decay, a sudden collapse from within, and the emotional reality of impermanence. Dark energy may dictate the fate of the universe, but meaning is something we create in spite of that, because the end of all things is not a reason to despair. It is a reason to cherish what is, while it is, to wonder, to witness, to live. We've mapped its fingerprints. We've felt its pull. We've watched the universe bow to its pressure. Still we ask, what is dark energy? Because naming a force doesn't explain it. Dark energy is a placeholder, a confession, a label for something we can't see, but must believe. But what if it's more than a placeholder? What if it's a field or a particle? What if the most dominant force in the universe comes not from stars or matter or motion, but from a ripple in the vacuum itself? One idea emerging from quantum field theory is that dark energy may be caused by a scalar field, a type of field that assigns a single value to every point in space. Unlike electromagnetic fields, which have direction, scalar fields are simple, featureless, and powerful. We've seen one before. The Higgs field gives particles mass. It pervades all of space, changes the rules of physics depending on its value. Could there be another scalar field at work? One that isn't responsible for mass, for acceleration? Physicists have proposed names for this hypothetical entity: quintessence, phantom fields, k-essence. Each of these theories imagines a new kind of field rolling slowly across the universe, changing with time. Unlike the cosmological constant, which stays fixed, these fields evolve. They are dynamic, alive, whispering through the void. And in some versions, the field is associated with a new particle, a boson, so faint, so elusive, that it has never been seen. A particle made of nothing that pushes on everything. This is not mere fantasy. It's a response to a deep problem in cosmology. Why is dark energy so small, yet not zero? Why did it begin to dominate the universe's expansion only recently in cosmic terms? This timing problem is sometimes called the cosmic coincidence problem. Why now? Why are we alive at precisely the epoch when dark energy becomes important? A dynamic field could help answer that. In quintessence models, the energy density of the field decreases over time. That means it may have been irrelevant in the early universe and only now reached a point of dominance. The timing is not perfect, but it's better than chance. These models also allow for future evolution. Perhaps the acceleration will stop. Perhaps it will reverse. Perhaps a cosmic contraction lies ahead after all. But there's a cost. These fields are speculative. They require new physics beyond the standard model, new symmetries, new particles, new constants. And so far we've found none. No signal, no detection, no experimental proof, just models, equations, clues, and the quiet knowledge that we may be missing something essential, something fundamental. In this final segment of the section, we go deeper into the speculative horizon, where mainstream physics meets the edge of imagination. We'll explore theories that suggest dark energy may be tied to extra dimensions, holographic principles, or even information from beyond our observable universe. For some physicists, dark energy is a whisper from within, subtle field. a lightweight particle, fluctuation of the vacuum. But others look further, beyond particles, beyond fields, beyond even this universe, and ask, what if dark energy is not a thing at all? If it's a signal, a side effect of something deeper? One theory is that dark energy is not a force, but an artifact, a consequence of the way we're interpreting space-time. This idea comes from the holographic principle, the notion that everything we perceive in 3 dimensions may actually be encoded on a 2-dimensional boundary, like a hologram projected from a distant surface. If true, then space, time, even gravity itself may be emergent properties, illusions that arise from quantum information stored on the edge of the universe. In this view, dark energy could be residual tension in that information, a kind of cosmic back pressure caused by how space-time emerges, not a substance, but a bias in the code. Other ideas reach into extra dimensions. In some versions of string theory and M-theory, our universe is a 3-dimensional brain floating in a higher dimensional space, sometimes called the bulk. Gravity, uniquely, may be able to leak into or feel the effects of these extra dimensions. Dark energy in this picture might not be our energy at all. It could be energy bleeding into our universe, or something from beyond, tugging on the edges of our space like a hidden tide. Imagine a balloon being inflated, not from within, but from pressure applied in a dimension we cannot see. Could dark energy be the shadow of an interaction we are not equipped to witness? It would explain much: why it is everywhere, why it cannot be detected directly, and why its effects are felt only on the grandest scales. It would also mean we are not alone, not in the sense of life, but in the sense of structure. That our universe is not all there is, but a membrane, floating in something larger. And then there are theories even stranger. Some physicists speculate that dark energy could be a correction term in our models, rising from misapplied symmetries, hidden variables, or even simulation constraints. If the universe is not fundamental, but programmed, if reality is an emergent computation, then dark energy may be the byproduct of a boundary condition, a runtime adjustment, a global parameter set not by nature but by design. We explored this idea more deeply in the dark equation, but it bears repeating. Dark energy behaves less like matter and more like a rule. It does not react. It does not change. It applies everywhere, always, with no exception. That's not how matter behaves. That's how instructions behave. And so, we are left with a question not of physics, but of ontology. What is this force that acts like nothing, but sculpts the everything? We don't know. We have models. We have data. We have names. But dark energy remains a mystery. A pressure with no source. A presence with no face. A field with no particle. A rule with no origin. And yet, is the most powerful force in the universe. Whatever it is, it's the reason the cosmos is growing. It's the reason galaxies are drifting apart. It's the reason the sky is darkening. It is the silence between stars. The expansion between atoms is the soft force behind time itself. In this part, we explored the most speculative and most profound ideas about dark energy, as a scalar field or particle, as a holographic tension from the edge of space-time, as gravity leaking into extra dimensions, or even as a rule set by the architecture of a simulated or emergent universe. Dark energy may not be matter. It may not even be energy. It may be structure, the shape of what lies beyond what we can see. Let's begin the final part of this journey, Part 8. Meaning in the pull. We have reached the end of knowledge. And yet something remains. We have mapped the void, studied the light, measured the invisible hands shaping the stars. We've looked forward into silence and backward into fire. We've seen how the universe may fade, fracture, or collapse. And now, what's left? Only the question that matters most. What do we do with all of this? What does it mean to live in a universe governed by emptiness? What does it mean to feel love, fear, joy, and longing? In a cosmos where the dominant force is not matter or light, but a pull from nothing? Dark energy is not personal. It does not know us. It has no agenda. It stretches the fabric of space without malice or purpose. It expands the distance between all things, simply because that is what it does. And yet, it shapes our destiny, our cosmic fate. our sense of scale and story, is the reason why one day the night sky will be empty. The reason why every distant galaxy is slipping away now and forever. It has no name, no face, no particle we can hold, but it has become the author of the final chapters of existence. And so we must ask, how do we live in a universe that is expanding, not just in space, but in isolation? The poet might say that we live in exile, that the stars are retreating and we are left behind. The philosopher might see it differently, that this is the very thing that gives life its urgency, its beauty, its fire, because impermanence is not emptiness. It is the canvas on which meaning appears. The stars will go, the galaxies will fade. But we are here now, not just to witness, but to feel. To build meaning in a universe that doesn't hand it out. To cherish connection while we have it. To make art in the silence. To ask questions in the dark. Dark energy pulls the universe apart. But maybe that's what gives our actions weight. In a cosmos that will forget us, every act of kindness becomes a kind of resistance. In a world driven by separation, every attempt to connect is an act of courage. And in a universe filled with silence, every word, every story, every breath is a kind of light. You may ask, why care if it all ends? But that question misunderstands the miracle, because it all ends, and still you care. That is the miracle. That is consciousness. That is wonder. That is the gravity of life in the presence of cosmic indifference. Not despair, but dignity. Not fear, but freedom. To live not forever, but meaningfully, now. In this final chapter, we explored the emotional implications of a universe ruled by a force we cannot see. How absence, separation, and silence are not the end of meaning, but the beginning of it. And how wonder, connection, and presence remain sacred, even as the cosmos slips away. We live in the pull, we rise in the stretch. In the face of dark energy, we are the ones who choose to create gravity of our own. It began with nothing. No stars, no time, no space. And from that, nothing, came motion. A breath in the void. A universe unfolding. We looked for answers in the galaxies. We found only questions in the dark. Something is pulling the cosmos apart. Not a force, not a storm, but a pressure that does not break, only drifts. We called it dark energy. But it is more than a name. It is the shape of our forgetting. We thought gravity would hold us, that the universe would slow, return, rest. But instead, it expands, and expands, and expands. The stars retreat, the filaments stretch. The night grows quiet, and what remains is not destruction but distance, cosmic solitude, a soft unraveling. And yet, in the middle of all that drift, we live, we ask, we learn, we imagine. We create firelight against the cold, stories against the silence, wonder against the void. We are the brief moment that knows the universe is expanding. The one breath in time that asks, why? And that is enough. Because dark energy may shape the fate of space, but it cannot unmake the miracle of presence. And as long as we are here, the cosmos has a witness. The silence has a voice. This is cosmic canvas, where the universe is not only studied, but painted in meaning. Till next time, keep asking, keep looking up, and never stop wondering.